Hello class, welcome to our 6th video for the course. Today we're going to be talking about truth tables again and comparing them, using them for arguments. This is one of a series of videos. I believe our next lecture has to do completely with arguments, and then our third one will be looking at formal argument forms and truth tables, all of which is material that will be tested on your midterm coming up. Will be open the 19th through the 23rd. I'll post an announcement for the midterm on the 18th, giving you details and all of the information that you need to be successful with regard to the midterm. So, putting all that aside, let's get started. So, what we're going to be doing again today is truth tables. Recall that when filling out a truth table, what we want for our two predicate variables is all of the different assignments of possible truth value. And the way that we do this is we set 2 to the nth power, where n is our number of predicate variables. In this case, we have 2. We have phi, which is the circle with the line through it, and we have psi, which is this trident-looking thing. I'm going to be using these terms quite a bit in this lecture, phi and psi, so keep in mind phi, circle with a line through it, psi is the trident-looking thing. These are Greek letters used in other logic courses, and especially more advanced courses, so having a bit of a familiarity with them, even if it's just an example, will help you, hopefully, going forward if you become interested in logic and you'd like to pursue it further. Okay, so to get all of the possible truth combinations, we take 2 to the 2, which is 4, and so our truth table is going to have 4 lines going down, and we're going to alternate. So we're going to start with true, true, false, false. So we have our 4 lines, and I've alternated 2 and 2, and now I'm going to change up the way in which I alternate. I'm going to go true, false, true, false. Now, given these 4 lines for our 2 predicate variables, we have the full combination of possible truth values when we mix these 2 predicate variables together. So we have a line where both are true, we have a line where one is true, one is false, another line like that except inverted, and then finally a line where both are false. And then we're going to fill out the rest of the truth table. So when filling out a truth table that's more than just one operation, what we want to do is we want to identify the main connective. Our main connective is the operator that has the most scope, which is, in this case, the conjunction or the dot. So it's going to be the truth values under the dot that are important for this particular truth table. We should recall from last week's videos that the truth conditions for a conditional, if phi then psi, is that it's true when both the antecedent phi and the consequent psi are true, false when the antecedent is true but the consequent is false, right? You can't have a true then false. And then it's true in every other situation, right? So true, false, true, true. And that is for the part of the truth table that is under a conditional. Now, this conditional is being operated on by a tilde or a negation. And what negation does is it flips all of our truth values. So we're going to take everything that's here and we're going to negate it. So true becomes false, false becomes true, and likewise true becomes false. Okay, but we're not quite done yet. We still have one more operation to manage, which is our conjunction. And just for the sake of clarity, I do this because I don't want to be looking back and forth. I'm going to take phi's truth values and then write them underneath phi. So true, true, false, false. And now what I'm doing is I'm comparing the truth value here with the truth value here. And I know that for a conjunction, it's only true when both halves are true. There's one line, and it's the second line where both options are true. So that's going to be true, and the rest will be false. Now, when doing a truth table that's complex like this, one really important trick, and in fact, it's not even really a trick, it's just what's done, is underneath the main operator, we're going to circle or highlight or draw a square around the truth functions that matter. All of this stuff is just like scratch work. The stuff on the side, this is what matters, this particular column of truth values. And so we put a square around it. And that is false, true, false, false. Okay, now you'll notice that I've written up a few other predicate equations over here. We're going to use those in just a moment. But before we do, I want to talk about the terms from this section of the book, which exist here and here. So on this side, right and left is weird with videos. I don't know how to tell what's what. It inverts and flips. Who knows? So on this side of the board, we have our... Sorry, the video cut off. I got a phone call. Let's resume. So on this side of the board, we have our terms that indicate features of truth tables atomically, just by themselves. And on this side of the board, we have our terms that help us to define truth tables in comparison with one another, which is why I've written down these other predicate equations. We're going to be comparing truth tables. So first, a tautology. A tautology is a statement that's always true, something like P or not P, right? It's either the case that it's raining or it's not raining. That's always true. It's either raining or it's not raining. Either something exists or it doesn't. Again, this is a tautology because everything either exists or doesn't exist. So for a truth table, a tautology is going to be some statement whose truth values under the main connective are all true. Every single one is true. So if we have P or not P, and over here, so we're going to do a truth table. Again, there's only one predicate variable, so we only need two, true and false. We only need two truth functions, right, to get all the possible combinations of truth functions, which is just either P is true or either it's false. So if P is true, we can write that here and we can write that here. And then the tilde makes it false. If P is false, we'll write that here and we'll write that here. The tilde makes it true. But we know of a disjunction, given our last video, that the disjunction is true anytime one of the operations is true. So I'll write true here, and then I'll give a box to indicate that this is the line of the truth table under the main connective, the one that we're inquiring on. And it turns out that every truth value under the main connective is true. Therefore, P or not P is a tautology. Okay, great. So tautologies for truth tables are when all of the values under the main connective are true. This is the opposite in the case of a self-contradiction. In the case of a self-contradiction, all of the values are going to be false. So what happens if we replace this disjunction with a conjunction, right? We still have the same truth values. P is either true or false. So I'm going to write that here, true and false. And then again, our tilde changes the truth value. But we know that conjunctions are only true when both values are true. Okay, so this one's going to be false because we have a true and a false. And this time we have a false and a true, so it's also going to be false. I'm going to draw my square. And all of the values under the main connective are false. Therefore, this is a self-contradiction. It's raining and it's not raining. The thing exists and it doesn't exist. This is impossible. It's a contradiction, a self-contradiction. Great, okay. And then a contingent statement is just one that has both true and false, but definitionally speaking, a contingent statement or a contingent truth table is a truth table with at least one true line. So turns out that the truth table that we began with is contingent because this line right here is true, the rest are false. So there's one possible case in which that statement runs true, the rest it's false, so it's contingent. Okay, so these are how we classify truth tables atomically or by themselves. These words, or these phrases, are how we classify the relation of truth tables with one another. So logical equivalence, and I often abbreviate this as logical EQ because it's easier, so I accidentally wrote the Q in capital letters. Oops. Logical equivalence is when truth tables have the same exact truth values. Truth tables contradict each other when they have opposite truth values in every line. Truth tables are consistent when they have at least one line where the truth values are the same, so one line where both truth values are false, or one line where both truth values are true, or multiple, right? It can be consistent in many different ways. And then inconsistent is where the truth values are not shared at all. So like a tautology versus a contradiction or something of that nature. Let's do the truth tables for these statements, and then I'll use them as examples to point out consistency, inconsistency, contradiction, equivalence with regard to the truth table that we began today's lecture with. So we know that for the disjunction phi or psi, and again for these we can use our truth values here as reference points, that the disjunction is true when at least one of its conjuncts is true. So it's going to be true in the first case, it's going to be true in the second and third case, and then when both are false, it's going to be false. In this case of disjunction, if we're to compare this truth table with this truth table, we'll see that there is consistency. It's not a contradiction because the truth values are shared in certain cases. They're not always opposite. Again, it's not equivalence because they have different truth values here and over there. But there is at least one line, and that's the second line here, where the truth values are the same. And so this truth table is consistent with this truth table. Okay? And then over here, we're going to do not psi, which is going to be false. And again, I'm just taking the opposites of all of these values. So false, true, false, true. And then we know that the conjunction, which is our main operator, our main connective in this truth table, is, and just for the sake of clarity, I'll write down true, true, false, false to match phi here. We know that the conjunction, our main operator, our main connective, is only true when both of the conjuncts are true. So it's going to be false here, it's going to be true here, it's going to be false, and then false, because again, the second line is the only line in which both of our predicates are true. And again, I'm going to draw a big square here to note the main connective. This is the line we're interested in. And if we notice, false, true, false, false is equivalent to false, true, false, false. So, logically speaking, in terms of truth value, this statement is logically equivalent to this one. They mean the same thing. They are telling us exactly the same stuff. They might be telling us the same thing in different ways, but broken down to the atomic truth values, they're exactly logically equivalent statements. So even though rhetorically they may translate differently, logically they are exactly equivalent because their truth values are just the same. So we have logical equivalence. Okay? And then we know that our truth value for, or our truth table for the conditional, the material conditional, is true, false, true, true, where it's true in every case except when the antecedent is true and the consequent is false. This is a case where true, false, true, true is the opposite of false, true, false, false. And so this truth table, because it has the opposite truth values as this one, is a contradiction. It contradicts our truth table up here. These are opposite meanings. This says it's raining and this says it's not raining, or something like that. That they are in contradiction with one another. And then finally, we have our biconditional, which we know the truth table is true when both of the values are the same and false when not. So both of the values are the same when they're true or when they're false, which is the first line and the fourth line. But they're false when the values are different, which is the second and third line. This truth table is not the same as the first. It's also not the opposite of the first. But importantly, it doesn't share any common truth values with it. And so this fourth truth table is inconsistent with our first truth table. And that's because it shares no truth values in any of the lines. First line, true to false. Second line, false to true. Third line, false. Oh, it is consistent. Oh, my bad. It is consistent. So, but you get the point. If this truth table were such that it didn't share any truth values with the first, then it would be inconsistent. I messed up. Turns out that there is a line where they both share a truth value, and so they are consistent. That was just my bad with coming up with examples on the fly. Hopefully that's not too confusing. If you don't get inconsistency, it's just the opposite of consistency. Let me know. I'm happy to answer questions. Great. Okay, so that's this lecture. We'll move on to the next section.